Hello and welcome to Mathematics for Everyone, where we are going to talk about classifying in mathematics, what we mean by it, what it's used for, etc. First, we're going to start off lightly, and I want to sketch what the idea behind classifying something is. Let's say we have a bunch of people that we all want to kind of identify. They all have different attributes. They may have a different height, they may have a different hair color, they may have a different eye color. All these things may be different. And usually, we are not interested in a person as a whole because a person is made up of many, many things, many, many attributes. For example, their hobbies and their interests in general all attribute to the person, but sometimes we're not interested in that. For example, if you are in a hospital or something like this, you're not really interested in what your hobbies are. Just maybe you're when you were born, or maybe how tall you are, etc. So in this sense, sometimes people are reduced to essential information that is needed for a specific context, as well as, needed in a given moment. For example, if you're out on a date and you have never seen the person before, but you know they wear glasses, so you know that you can rule out those that don't wear glasses. This is what the idea of classifying is about. Let's sketch that for a bit. We start with a set of things, and usually want to identify essential information. This is usually because it's easier to save essential information, as well as there's just not this huge clutter of information that you have to keep up with. So this is a good idea. For example, we could classify a person or just any human being, right, to the day of the month they were born in. Maybe not the year, but just the day of the month, right? So what we could do is we take the set of all different dates in the year. Let's say the 1st of January, whoops, the 2nd of January, till we reach the 31st of December. So what we could do is we start with these dates, but we are usually just interested in a specific birthday. So what you could do is you could basically cut it off here, then here, for each and every single date. What happens is you transform this one set into multiple little sets, which we can visualize as containers. So basically you have this box. This is the box for all the people that have their birthday on the 1st of January, right? Next to it, you have the box for all the people that have their birthday on the 2nd of January, and so on and so forth. In this way, you don't have one set, but rather you have 366 sets because of the leap year. So we've come from just one set of any date suits us to 366 sets where we can distinguish between each and every single date in the year. This means we start with some humans and we start with some dates and we want to identify the essential information. In our case, the essential information is the day of the birthday, just as the day of the month, which means we have to know when the person was born, which means we have to basically save the information for each and every single day, which is why we reached this conclusion with 366 buckets, basically. We could have done this differently too. Maybe we are not really interested in the day of the month. Maybe we're just interested in the month. So what you could do is you don't have to cut after each and every single day, but rather you cut after each and every single month. So this bucket might be for all the people born in January. This bucket might be for people born in February, and so on and so forth. This way, we end up with 12 sets. So 12 buckets that we can use to classify information. But there's, again, something interesting we see is that this had just one set, like every single day is just in one container. So basically we start with all humans, and then we split them up for each and every single day, which means we sort them, right? So this is a sorting, which means we gain information. But if we go from every single day separate to just every month, we lose information. And this is interesting because every single day gets put into, or not every single day, but every single day of the month get put into this same bucket. Which means if both of these stick figures were in this bucket respectively and in this bucket respectively, afterwards we couldn't distinguish between these. We just know that they were born in January. In this way, sorting information and classifying is a way of keeping track of how much information do I actually have. And also in this way, there's this interesting development of this is a fine sort of way to handle information because it requires more information. And this is what we call a coarser. Sorry, which this is coarse. This is just not as fine. We lose information when we go there. Mind you, we still gain information from just everybody because we know when they were born, at least in what month they were born. But we kind of lose information in terms of when exactly. You could go even further and say, well, maybe we just have, we not only have each day of the month, of each month, but also every single minute of the day. You could make this even finer if you wanted to. So, what have we learned here? We have sorted information. Let's not say we've sorted information, but we have sorted objects. In our sense, human beings, but just as an idea object, right? By some similar attribute. Another interesting question we can ask is, well, do we need all this information? Do we need all 366 buckets up here? Maybe there's just nobody who's born on the 3rd of January, for example. That means we can drop the bucket. We don't care about the bucket. Which means we only care for non-empty buckets. This means there should be at least something, right? But since we are using information in the sense to distinguish two people from one another, there should never be one single person who is in two buckets at the same time, right? There should never be something like this because then I can't identify based on the attributes I have. So there can't be a person who was born on the 1st of January and the 2nd of January at the same time. Which makes sense. as long as like the birth doesn't go over the, you get what I mean. But still, like we can justify the claim that there should only be one accepted date of birth, which means there shouldn't be any overlap in between the buckets. But that's not all. Not only should there not be overlap, and every bucket should have something in them, but also we have to have enough buckets, right? So all the buckets put together have to give everything. Because if we sort human beings, for example, some subset of every person living in the United States, for example, we can just sort them by their date of birth, but afterwards, every single person has to be put away somewhere, which means we never skip anyone. So, what we could say is every object should be accounted for. This way, we have every single object somewhere. We know that we only have buckets that are non-empty, and there's no overlap, which means for every single person there is, we can ask, what bucket are you in? And they will only give us one answer, which is the answer, which is the information we are interested in. Some other example. So what could we do? We know that every object has to be accounted for, there should be no overlap, and we only care for non-empty buckets. So let's say we are interested in height, right? Height of human beings. We could start and say, well, we start at 0 centimeters. It's reasonable. Then 1 centimeter. And if we just assume that there are only ever just natural numbers in terms of height, then there's nothing in between, so we don't miss anything. So we round up, if that makes you happy. But is there ever a human being that is just 0 centimeters or 1 centimeter, assuming they were born at some point? This probably isn't the case, because after a person is born, they usually start around like somewhere in the 2 digits. So we probably don't care for this bucket, and we probably don't care for this bucket. Although it is good that we thought of these buckets, because we have to have every single object accounted for, which means we can't be neglecting anything else. But let's say there's something like, I don't know, 35 centimeters. Let's start here, and then we go up to some large amount, let's say 3 meters. And let's say everything in between is accounted for. Who knows? Maybe this is not empty. I have no idea. Could have been, right? So there's a person in here, and there's a person in here. I'm sorry for this person. For this stick person here, at least. Alright. So, is this list exhaustive? Well, we could ask, is there a person that is not accounted for? And I think every human being should fall into this range, hopefully. If not, then I'm being neglecting, which is not good, but happens. Is there no overlap? Well, as long as we say that no human being can be 1 meter and 1 meter and 1 centimeter at the same time, then yeah. Of course, people can move in between when they grow, but they cannot be in 2 buckets at any one single point in time. And, well, is there just non-empty buckets, which we assumed to be the case because we've neglected the ones that are unlikely, to say the least. But what kind of set did we choose? So basically we looked at height. So let's say 35 centimeters, I will drop the centimeter, up to 300. And we can cut them off after every single centimeter to get the buckets. But you could also have ranges. For example, you could have 35 centimeters up to 75 centimeters. And then 75 or 76 centimeters, sorry. Because buckets can't be overlapping, which means if I had 75 again here, they would be overlapping. Oh wait, I said I dropped the centimeters. Oh, up to 125 and maybe like this. I have no idea. Maybe like 250 up to 300. They don't have to be all in the same range. It doesn't really matter. What matters is that none of the buckets are overlapping. Every object is accounted for, and there is no empty bucket. In this way, every person that was in this bucket, and then the bucket next to it, and the bucket next to it, and so on, until the bucket that is labeled 75 is put together into one group, which maybe we care about. Maybe we don't care about their individual height, we just care about their range of height. So what this whole idea gives you is a ranking of information, so to speak. You can be very precise. Maybe you don't want the buckets that just say 35 centimeters, but you want buckets that say 35.2 centimeters, and so on and so forth. You can be very specific with this, but as you can see, the more specific you get, the more information you have to store, because you have way more buckets and the same amount of people, obviously, but you still have to save somewhere what person is in what bucket. So this is the mathematical concept of what is called an equivalence relation. And I don't want to go into detail of what the mathematical definition of an equivalence relation is at this point in time, but I will write it down if you want to look it up in Wikipedia or something. So this is an equivalence relation, where this gives rise to an equivalence relation. Because now we can take two people and ask, hey, what height are you? And if they say, well, I'm 1 meter and 70 centimeters, and oh, that's the same height as me, then they belong to the same bucket. So they are related in a sense. This is where the idea of a relation comes into play. They are related because they're in the same bucket. Now we're going to step this up a notch. We're going to get more mathematical. Let's talk about this in a more mathematical setting. Let M be a set, which means it can be written with curly brackets and some objects in them. But it could potentially be infinite, maybe like the natural numbers or the whole numbers or whatever you like to imagine there. Now, we have to translate this information up here, right? We only care for non-empty buckets, and we care about some attribute. No overlap has to be between the buckets, and every object has to be accounted for. Let's write that down here. Only non-empty buckets. Then we don't want overlapping buckets. Let's just say no overlap. And every object has to be accounted for. Whoops, I don't know why I wrote that. What does it mean that something has non-empty buckets? What does it mean that there's no overlap between buckets? And well, what do we actually mean by a bucket in our case? Well, as we've seen before, we had the whole year segmented into sets. For example, each and every single day belongs to a singular set where we said, well, we really care about what day of the month you were born in. But we could also say we only care about the month like January, February, and so on and so forth. So what we've done, if we have taken subsets, and this is what we will call a bucket in this sort of sense. A bucket would be a subset. And we will call these buckets Mi, where n is a natural number and I ranges somewhere between 1 and n. We're not really dealing with infinitely many buckets, we only deal with finitely many, which makes sense, right? We can sort infinitely many things, like, for example, imagine if there are infinitely many people, but they still have to be born on some day between the 1st of January and the 31st of December. So, well, those are only finitely many options. But now we have to ask ourselves, what does it mean for this bucket to be non-empty? Well, mathematically, this would translate to Mi not being an empty set. What does it mean is that there's no overlap between the buckets? Well, this would translate to Mi and Mj having no intersection, as long as I is not equal to j. And what does it mean that every object has to be accounted for? Well, the whole set has to be obtainable in the means of union or unionizing, or whatever, all the different MIs, all the different buckets. If I throw all of them together, I have to get the whole thing. And this is an ideal, for me at least, in the way of thinking about it, ideal representation of an equivalence relation, equivalence class, whatever you want to say in this kind of this notion. So if you look at equivalence relations in Wikipedia, hopefully you will find something like this as well. But now, where does mathematics start, right? Mathematics started with our idea of translating here. This idea here. Yeah, let's use blue. This was math. This was math. All the other things, basically using the formulas, etc., is good, and of course it's part of mathematics, but this is where math happens. In translating between what we have in mind, that we only want non-empty buckets, and what this means in the language of mathematics. Now, mathematics or mathematicians are interested in these equivalence relations also because numbers numbers share certain attributes, and usually we are interested in certain attributes of certain numbers. Let's say we take whoops, no, no, this is not, no, that's not what I bargained for. Oh, okay, thanks. Let's take the whole numbers, all the way from negative infinity up to infinity. And as you can see, this is not a finite set. How do we sort through this mess? How do we make appropriate buckets? What kind of information do I want to obtain from this? And well, we can start quite naively, actually. Let's just list them out and see what happens. Well, you could say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Ah, well, I think you get the picture, right? But I have to count backwards too, so -1, -2, -3, -4, -5, -6. Well, those are infinitely many still. Like, what do? We can actually just look at these. Look at the columns. Let's color them differently. I love purple, so I use purple. Okay, let's use green. Green's cool. So what we've done is we've listed in this kind of schematic sense every single number in the set, but now we group them together by their column. This means we have the set that contains -6, -3, 0, 3, 6, so on and so forth. Oh, and well, I guess to the -2. Then -5, -2, 1, then 4. Sorry, I had to look. 7, and so on and so forth. Then -4, -1, 2, 5, 8, and so on and so forth. Now we have to ask ourselves some questions. Is this not empty? Yes, this is not empty. Is there any number that appears in both of these? No. So, no overlap. And last but not least, is every single number accounted for? Well, I can find every single number that's here. So yes, this is indeed accounted for, which means the set of all numbers can be obtained by, well, I should at least do some 6 minus 3, 0, 3, 6. And take this with the union, and the union, this is only another one, but I'm a bit lazy. -4, -1, 2, and so on and so forth. Everyone is accounted for, there's no overlap, and we don't have any empty buckets. And maybe you can see where this is leading. You can think about these numbers in terms of steps by 3. This is the way I've drawn them too. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then 3, 2, 1, 3, 2, 1, and so on and so forth. You have to kind of swap the orientation with it, like 3, 2, 1, and so on, because you go into the negatives, right? If you think about the number line, then this makes sense. Kind of flip over. But what does this resemble? As I said, it's going in steps of 3, but what we also, how we can look at this is that this set, let's call it 3 times the numbers, the whole numbers, and we will see why. This set contains of all the numbers that are divisible by 3, which means that then they can be represented as a multiple of 3, such that k is a whole number. And this can be represented can be represented as a multiple of 3 plus 1. And I think you can already guess what the last one is going to look like. This one The last one can be represented as a multiple of 3 plus 2. I'll let you work it out. So what the information is, like, I'm sorry, that was not a sentence. The information that we recovered during doing this procedure is basically what numbers are divisible by 3. This is this one. What numbers are divisible by 3 after subtracting 1, which means they have a remainder of 1, and what numbers can be divided by 3 once we subtract 2, which means they have a remainder of 2. This is what we call modular arithmetic. But there's a usual representation of modular arithmetic, not in this column sense, but rather in a clock sense, because the fingers on our clock tick around, and every 12 hours, for example, they tick over. They go from AM to PM, right? So how we can think about this is we start with a 0, then a 1, then a 2. It's a bit, sorry for my bad drawing. It's basically like this. 1 or 0, 1, 2, 3, 4, 5. So we can extend this. Okay, I didn't quite think this through. So we can continue with 6, 7, 8, and so on and so forth. So you can go round and round and round like a spiral. Oh, this is getting messy. Alright, let's not do this. So you can go round and round and round. And in this way you can see how all numbers are divided into 3 parts. This is also another good way of looking at these buckets. Because in this way, every single number is accounted for, but they only belong to one bucket. And it's in 3 parts. But I like to visualize it in a little different way. Because we see this column structure, and I like to think about myself as being an observer that is looking at all the numbers from up top, right? So let's sketch that down here. So bird's eye view. Right? This would be this. 0, 1, 2, 3, 4, 5. And then minus 1, minus 2, minus 3. And then this. So this is if you look from up top. And when you take this nice little bucket approach, you just change your angle. You're not looking at it from above, but you look at it from this kind of, coming from this kind of perspective. So you don't look at it from the top, but from up front. So the way I see this is rather you have 0 here, the 1 here, and the 2 here. And, well, the 3 is just in the same way as, or on the same spot as 0. The 4 is just on the same spot as 1. The 5 is just in the same spot as 2. Then 6, then 7, then 8, then 9. Well, this actually looks pretty. So what happens is when you change your perspective, how the numbers are lined, then you end up with naturally 3 kind of lines, right? They are all in a queue, all behind each other. Mind you, this is an infinitely long queue, but that doesn't really matter. What matters is our perspective on things. Because if our perspective changes, then we see what was infinitely complex before, all these different numbers that we have to memorize. Now we only have to memorize how to count 1, 2, 3, 1, 2, 3, because we've changed perspective. And this is a neat little thing that wouldn't necessarily be connected to the bird's eye view here, but this is rather, I'm sorry, this got a bit messy. This would be like a front, oh, I should write this here. This would be a front view. No, this is not how you write front. This is better. And in this kind of, or viewing it from this kind of perspective, from this angle, you can easily see that there are only three main structures. The ones that are divisible by 3, the ones that have remainder 1, and the ones that have remainder 2. Why do we actually care about modular arithmetic? Well, or why do we care about this stuff in general, right? Let's say, if I write, no, this again, not how you write, that's better. If I write x is equal to 5, both sides, I assume that x is a whole number here, both sides have to satisfy the same properties. They are the same number, which means they behave like the same number. This might sound stupid, but I have the 5 here, right? My 5 is right here. So my x has to be here as well. X can't suddenly be here. That is not allowed. Like, what are you doing there? X has to be here as well, because x is equal to 5. So if I find out that my x is actually somewhere else, in a completely different bucket, then I screwed up. But screwing up in mathematics is not necessarily a bad thing, because if I started from a valid and good starting point and end up somewhere that is completely bogus, maybe I didn't make a mistake, but rather my assumption that I started with was just wrong. For example, let's look at the following equation. Let's study x squared plus y squared plus z squared plus x plus y plus z equal to 1, where x, y, and z are whole numbers. Now, this could be a daunting equation, and we are interested in, are there any x, y, and z such that this equation is satisfied? We could ask ourselves this question, but how do we go about proving this? How do we go about doing this? This is a question that is often asked in number theory, where we're usually asking for a solution of an equation with all the numbers or all the variables being whole numbers. You can also find some related information on Diophantine equations. If you Google it. So, how do we go about this? Well, as I've said before, the left side of the equation is a whole number, and the right side of the equation is a whole number, which means they have to behave in exactly the same way because they're equal to one another. If I find out they can be in completely different buckets, I'm screwed. I'm really screwed. So let's do this. Let's look and see if they all belong to the same bucket. Note to myself that 3 wasn't necessarily wasn't necessary. That's what I wanted to say. I could also have done like 1, 2, 3, 4, 1, 2, 3, 4, and basically order my numbers in pairs of 4, right? But I could also have done 5 or 6 or 7. It doesn't matter. It has to be the same everywhere. So, left side, no. I can salvage this. Oh, yes. Left side and right side always have to be in the same bucket. No matter how I sort. Which means it doesn't matter if I take 1, 2, 3, 1, 2, 3, 1, 2, 3, or 1, 2, 3, 4, 1, 2, 3, 4, and so on and so forth. It doesn't matter. So let's actually take it a notch down and just say 1, 2, 1, 2, 1, 2, 1, 2. What happens then? Well, we can just look at it, right? So 0, 1, 1, 2, and again 1, 2. So 0, 1, 2, 3, 4, 5, 6, 7. As you can see, this kind of bucket sorting leaves us with all even numbers and all odd numbers. This means that sorting by 2, in this sense, basically, yeah, segments, right? Segments the whole numbers. In terms of even and odd. But what is the interesting property if we only care about numbers being even or odd? This is not only a way of sorting things, but also a way of essentializing information and or reducing information such that new algebraic properties actually hold. What do I mean by this? Now, for example, if we look at an even number, or if we look at n, and if n is an even number, so let's do this in the table, or n is an odd number. What happens if we look at negative n? Well, if n is even, then n is a multiple of 2. If we swap the sign, this doesn't change. Minus n is still a multiple of 2. They are in the same bucket. If n is odd and we swap the sign, that doesn't change. Still, minus n is still an odd number. This means n and minus n are in the same bucket. Mathematically speaking, how we can write this is n is in some form equal to minus n when we sort using 2's. This sorting is called modulo, which is also where the name modular arithmetic comes from. Basically, n and minus n are just the same. There is no difference. We have no negative when we sort. What else don't we have? What else do we have? Let's look. If we have an even number and we multiply it with an even number, we obtain an even number. If we have an even number and an odd number, we obtain an even number. And if we have an odd number and an even number, just reversing the factors, we still have an even number. But if we have an odd number and an odd number, this leaves us with an odd number. So what is this, or how does this help us with n? Well, if we look at n, and n is an even number or an odd number, what happens with n squared? Because it's natural that we ask about n squared, because we have x squared, y squared, and z squared here. Well, let's look. N is an even number, and I multiply it with itself, which means it's still an even number, which means they are even. Well, look at n. N is an odd number. I multiply it with itself, which is an odd number, which means we have an odd number. This looks just like this one. So what we can conclude is that n is essentially the same as n squared when you look at this modulo 2. Even stays even, odd stays odd. But how does this, how can we combine this information, right? This is a natural question. Well, we have x squared plus y squared plus z squared plus x. So I can write x squared plus x plus z squared plus, well, let's actually not do z because that triggers me, y squared plus y plus z squared plus z, which is equal to 1. But if we look at this whole equation modulo 2, then, well, this stays odd because it's 1, it's just 1. But if we look at it here, we have the x squared plus x. Well, x squared is essentially the same as x, right? So this is basically just x plus x, or x minus x. No matter how you look at it, this will be an even number. We can discuss this again if you want to, but this becomes apparent just from the equations here, because we can write this, or we can just combine these to obtain n squared plus n is equal to n minus n, which is equal to 0, essentially, mod 2. But translated, it just means if you have an even number squared plus even number, it stays even. Odd number squared gives an odd number, plus an odd number gives an even number. And this doesn't depend on it being x, so this is even and this is even. But we have a problem. The left side is even and the right side is odd. How we could write this is x squared plus x plus y squared plus y plus z squared plus z is the same as 0 because it's even, modulo 2, and 1 is the same as 1 modulo 2. So if there were any solution to this equation, then it simultaneously has to be an even and an odd number. But this can never be the case because we've said that there can't be a number that is both even and odd at the same time, because buckets just don't overlap. We conclude there is no such solution. There is no solution. This is quite interesting, right? So just because we've looked at it through the lens of even and odd, we've seen that this can never be the case no matter what you plug in. It just can't happen. These equivalence relations or equivalence formulations from above with the buckets are not only interesting because they lead us to these beautiful results, but also because there's a huge geometric aspect to them. Let's look at this, because this is what I'm mostly interested in when talking about these things, is geometry and topology. Let's think about designing a game. I'm sure you've probably seen this game before, but you have a spaceship, and in the spaceship you have to kind of destroy asteroids, fly around and basically just shoot stuff. You can ask yourselves, what happens if you fly to the boundary here, right? What happens? Well, in the game that we are talking about, what happens is that you spawn on the other side. So you can go round and round and round and round. And what this means, in terms of equivalence relations, or in terms of the classes and buckets that we've talked about, this point, let's use actual color, this point is just the same as this point. They just don't differ. The same way, this point is the same as this point. But these are not the same. Same way, this point, oh my goodness. I guess there is a difference. I didn't know. Well, I guess I could have thought so. This point is the same as this point. But in the same way, that's an actual pretty color. Like, what? It's really cool. Oh, I'm sorry, I'm getting carried away. This point up here is also the same point as this point down here. Or, again, let's do it for one more time with my favorite color. This point here, the same as this point here. So what could happen is no matter where you fly, you always spawn on the other side. How do we visualize this? Like, of course, we can draw this as like a sheet of paper, basically, where you spawn on the other side. But if you think about it as a sheet of paper, what you could do to make ends meet is just that. Make ends meet. Glue them together. Glue. So what happens if you glue this side to this side is a cylinder. So this looks like this. I have, oh, wait. I guess like this, where the blue dot now lives here, for example, right? This looks about right. The green dot lives about like here. The pink dot lives like here, right? But we still didn't connect the purple and the dark blue dot. Maybe they are like here. Well, let's glue again. Glue. What happens if we glue this and this together? If you like exercise your mind like this, you basically have a something that you could use in the bicycle too, right? Just a tire, basically. So it looks like a tube. It has been put together like this, maybe here. So the pink dot would now be here, like this, right? No, that's not the pink dot, that's a purple dot. The pink dot may be like here, for example, around there somewhere. Blue may be here. Who knows? The other one could be here. So this basically is our game. This is three-dimensional. So what you could think about this little spaceship now is able to fly on this so-called torus. This means spawning on the other side on both ends actually gave us an idea of where the spaceship actually lives. It lives on a torus. It can fly around here and then here and wherever it likes. Wherever it likes. It can just go wherever it wants. But in this kind of situation, right, in this kind of formulation, you don't have to keep in mind, oh, you spawn on the other side. You just fly around. It doesn't really matter. So in this sense, you could produce a torus on a 2D surface, like here, right? Basically like a computer screen. But there's another thing that I want to talk about, and that is the following idea. of gluing together. What if we look at the disk? So this will be my disk, right? It's just, you could think about a CD. It's just a continuous like disk. It doesn't have like this middle part cut out or something. Now, what I'm interested in is this boundary here. And I want to make it such that this whole boundary becomes one point, just like here. So now we don't glue just 2 points together, but rather this entire line together. What happens? Well, think about it like this. You kind of bulge this in, right? So this is the disk in another perspective. So here we have the ring that is there. So we kind of bulge this in and bring the ends together. And we obtain this beautiful thing. Well, it's actually not too bad. I was expecting way worse. And then it becomes a single point. What we've done is we've taken something that is two-dimensional and we have transformed it into something that is three-dimensional. And how this dimension of an object changes when doing this sort of operation is an interesting question, and I will leave this open for now. What we've done is, mathematically speaking, we took the quotient space. And I urge you to look at some quotient spaces. There are some interesting out there. For example, you don't really have to glue them together like this. You could also glue them together in a different way. For example, if you don't want pink or purple, I should say, to lead there, but rather lead there, so sort of flipping around, green still leads, or this dark blue still leads there, but green kind of lives here, right? Oh, they're the same green. Orange leads from here to here, so they basically like swaps around. You end up at a totally different thing, and maybe you can find out what that thing is. So this is what we've done. We've taken the quotient space, but it looks kind of particular, right? And what I mean by particular is this was a circle, this was a disk, and this is a sphere. They are kind of the same thing, right? So this is kind of a sphere, but it's basically a ring. Now this is kind of a sphere too. It has like the ring and stuff inside. Now, how can we think about this? Well, since we've taken the quotient space here, the interior of this ball was empty. Because, well, we've bulged this out and there's nothing here. There's just nothing. If you think about a sphere that is completely full, so basically another sphere that is filled, and you take again the whole boundary. I'm sorry, this is not looking pretty. You take the whole boundary of the sphere and collapse it to one single point, you get something interesting. It's another sphere. And with this kind of equation, or with this kind of idea, I want to leave it at that. If you take the quotient space of a sphere by one dimension lower, you ascend, essentially, a dimension. Thank you for listening, and I hope you enjoyed the first episode of Mathematics for Everyone, where we draw little, cute pictures. And, well, this sounds a bit rude, but sort people into buckets. Well, I hope you enjoyed nonetheless. I hope you've learned something, and I hope you join me when we march onto episode 2. See you then.